Thanks. So, hi, I'm Frank. I'm a research group leader at the Forschungszentrum Informatik in Germany. So, my team is looking into visual and spatial learning for robotics in general, but more specifically for autonomous driving. I'm really happy to present some of our research here. Um, I will actually split the presentation to present two kinds of research which are somehow connected. So first, it's um, um, a project which I presented at a workshop at CVPR. It's about cross-modal domain adaptation using semantic parametric maps. And this research also was one of the projects which sparks a big project of our lab, which is releasing a new data set, which we just released at CVPR this year, and promoted it there. So let's dive into as I said, my lab is doing all kinds of research around autonomous driving. A lot of things are connected to especially vision, but also we are trying since 20 years. We can apply our software on our two autonomous driving cars. So since I think now 19 years, we are allowed to drive fully autonomously in multiple German cities. So we are one out of I think three or four university labs allowed to do that. And to drive our stack and our research forward, we do, of course, industrial projects. One of the most famous one is the Bertha-Benz drive of 2013. In our lab, there was also the Kitty data set released, which is I think right now the go-to voxel 51 data set multi-sensor um, multi-sensor data sets. Yeah, we are trying to publish open source frameworks. Like one of our most famous ones is the Lane 2 framework, which is the de facto standard right now for HD maps in autonomous driving. And of course, in all these years, we are trying to adapt our hardware to our current software and to the state of the art of sensor hardware. So in the last years, this brought a problem with it, and that's actually which sparked the research from the first paper I want to talk about. Every time you kind of change, we are, of course, we are a university lab, so we don't have an unlimited manpower to label um, to label new data. So every time we kind of change sensors, sensor suites, we basically either have to suffer a big domain gap for our sensors, or we start relabeling data sets. So a problem most of the people have today. So what we were looking into a few years ago was um, in which ways can we conserve the knowledge we have in one sensor setup and transfer it to a new sensor setup we have. And we were specifically interested in doing that if the sensor modalities are not similar. Of course, if I have a very similar new camera, it's not a problem. I suffer a little bit domain gap, produce for the fine-tuning of the models uh, um, a very limited amount of training data, and I'm good to go. But sometimes, because of the sensor mounting or the sensor modality, I have such a big domain gap that this is not sufficient. So what we were looking into is can we automatically generate maps? So basically drive around the city, drive as much as we want, and then automatically map semantic elements in the city so that we can just mount new sensors on our car, drive around again, back project it into into the sensor space of the new sensors, and by that self-supervised train these models for these very new sensors. Um, yeah, so basically that's, for example, one of our very old sensor setups. And now here you see one of like a new sensor box. And this, of course, has a few requirements. First, we need to be able to very, very well localize within this map. And the sensors need to be very well calibrated towards this local towards each other so that we can do it with real different sensors. So we are managed to do that, and that's how we kind of conserve knowledge, which we labeled once for one sensor setup to more modern sensor setups. And what I'm presenting you right now is how we did it, for example, from camera to LiDAR. Like um, the pipeline I'm showing you now is um, taking like from a open source data set, which is very well generalizing. In that case, it's mapillary vistas. It's trained on it's generated with images from a lot of different cameras. So it's well generalizing on basically most of the current of the modern cameras we use for autonomous driving. And so with that open source data set, we can train models for our cameras. Then we have an automatic mapping pipeline, which maps using geometric primitives like cylinders, surfaces, bounding boxes, all kinds of different elements in the world. And then we back project it into the LiDAR space. So what you see here is, of course, what do we need for that? We need the open source data set to generate pseudo labels on our sensor data, in our case now camera data. Then we need a very accurate multimodal SLAM to have our 60 pose like in a way that we can also back project elements which are like 70 meters away back into the LiDAR. And with these two, we do the parametric mapping. Then it looks like that. And in the paper, we only looked on three elements like traffic signs, traffic shields, and poles. The reason is these are especially small elements for autonomous driving datasets. So a traffic light is like 20, 30 centimeters in diameter. And you want to also recognize in 70 meters. So it's way more challenging than a lot of other bigger things. And that's also a reason why normally for LiDAR datasets, you don't have traffic lights in it. So we were thinking of, can we just transfer this knowledge to the LiDAR domain? And as I said, that's done by basically using the intrinsic, extrinsic calibration, the 6D poses to render the ground truth in the new sensor space. In the exact sensor space you actually want to train your model in. So it could be like, in that case, you see here range image like 2D LiDAR or also like 3D LiDAR or in the 3D space. Okay, so how does that look? Here you see in 2D rendered ground truth, which is completely automatically generated for this 360-degree LiDAR scans. And again, it's coming from a public, the knowledge is, there's no human label involved. The knowledge is coming like from a, I don't know, maybe 100-degree camera image data set. And here you also see like predictions based on a data set like that. So we basically, of course, it's a weak labeling process. But again, I don't know how many data sets have small elements like traffic signs, traffic lights in a LiDAR data set. So that's how we basically like, you can also see that as a pre-training. It's like how we train a sensor modality which does not need to have overlapping and which at the same time does not have any closeness in the modality, we can teach this sensor domain the knowledge of the other sensor domain. Here you see it in 3D. So this is just an example. So what we did is the full process is fully self-supervised. No human labeling is involved. We don't need the requirement of overlapping fields of view of the sensors, which is a requirement for most domain adaptation methods. And again, we don't need any closeness. What you see here is like was done on a custom data set. And that was one of the projects which sparked our interest in creating a new data set, a public one, which is also capable of doing research in especially this direction. Here, we just released this data set last month. It's the Kid Scenes multimodal data set. And this is only this was only one of the research gaps. We discovered that with the current landscape of data sets, you can't do research in that. So we did it with our custom data set, and we thought that's exactly a research gap we want to fill. So that's the second work I want to present today. The KidScenes data set. It's actually by Ph.D. Like the first authors are Ph.D. colleagues of mine. And yeah, let's dive into that one. Again, this data set is released since CVPR on Hugging Face. It's also included after a talk of mine at CVPR at the Voxel 51 dataset family. So you can check it out right there, or you just go to our website, kidscenes.com. So let's have a look on the dataset. What's the current landscape of multi-sensor autonomous driving datasets? So that's a little bit historic, so let's go quickly through it. So one of the famous first datasets was the Kitty dataset. Some say it's the foundation of like a perception dataset, which captures a lot of sensor modalities and later also tasks. Then after that came was some kind of gap for a few years, and then we had this data set which are bigger in scale and modality. See here examples like Newscenes, Argoverse, Waymo, Argoverse 2, all of which had some specific like focus, and scaled it way bigger than the previous data set did. And after that, like in recent years, we had very task-specific data sets. A famous one, for example, is of course like NewPlan for closed loop planning, Waymore E2E, or OpenLane V2. Like we are especially interested in maps for autonomous driving. So OpenLane V2 was the first one which like really had like lane topology reasoning and sparked research in models which like care about lane topology, which is still very relevant for a lot of autonomous driving tasks. So the question is, isn't that the end? And another way how you can have a look on the autonomous driving datasets is they are not really equally distributed in the world. Like most of the modern datasets are either in North America or Singapore. So for example, I'm doing research in Europe. The street geometry and like road outline in Europe is way different. So if we find we also need datasets to fine tune or to train models to perform good on our streets. Another thing, for example, which is missing a lot in the datasets is like very accurate maps. So things which are missing in maps of Argoverse or new scenes are like stop lines and real 3D traffic light, traffic signs. And yeah, a lot of relational elements. So also the connection between a traffic light and a lane is highly relevant to know like I'm in this lane, so this traffic light shows red, so I actually need to stop. Yeah. So what are the major points in this data set? So first, it's a labeled multi-sensor data set in Europe. We deliver detailed and complete drivable HD maps. We come to the drivable later. We have accurate and high resolution sensors. And we have a lot of different highly complex urban areas with trams, also bike lanes, roundabouts, and so on. So not only highways. So that's like basic, a very basic description of the data set we released. So let's dive into the first big, the two major points we were working on. First, the sensor setup. So you can have a look on the detailed sensor setup, like on kidscenes.com or on our paper. But we have like 7 cameras which record more than 70 megapixels with 10 hertz. And in contrast to most of the other data sets, which are like rolling shutters, we actually have global shutter cameras, which is highly relevant for all like scene reconstruction tasks. Then we have LiDARs, which can look up to 500 meters, which is a big distinction towards other data sets. Also here we have 7 LiDARs delivering more than 1.2 megapoints per with 10 hertz. But yeah, so here is like a comparison, as I said, like we are one of the only ones which actually have global shutter cameras. We we have more than 70 megapixels with 10 hertz. Yeah, you can have a deeper dive into that, but as you see, only like at the megapixels, you see that we are magnitudes better than most of the other data sets. And also like one very specific thing is our LiDAR range, which is also like a factor 2 better than most data sets out there. So yeah, here, for example, is like the LiDAR distribution of a lot of the current data sets, which most of them um, only having a range of 200 to 250 meters. So the other very, very specific thing is what you see here. Look on the video. All these labels are globally consist from a globally consistent map, and they are back projected and are up to pixel accurate. So our whole mapping and labeling pipeline is that accurate, and this is like we have this like for up to 2000 scenes that we have maps which represent the cities, and we know our 60 location that accurate that you can basically have a very small element from the map back projected in the sensor space of any of our sensors. They are very well calibrated to each other. And this is like a magnitude of accuracy you don't find at other autonomous driving data sets right now. Yeah, so from when it comes to the map, we have like 3D traffic signs, lights, poles, and we have the full topology. We have real planning maps, and we actually validate these planning maps by driving on them. So we have let me have a look on the watch. Okay, the clock. So we actually have an auto-aware driving stack, and we use maps for driving, and we can closed loop simulate, like no, not simulate, we can closed loop drive on our maps, and it's we haven't verified all the maps yet, but that's what we want to do, and I think we are up to 60% of like um, having all maps driven. So that's another way of like really verifying if the maps are correct. So I told you first about the cross-modality domain adaptation with maps. That is one research which can, with this data set now, be done by researchers, even if they don't have the possibility to collect their own data. But there are other research which is also specifically sparked by the KidScenes dataset. One thing we talked about is like um, the relational HD map perception. So up to now, map perception means basically most of the time you predict a fixed set um, of instances with a specific number of points. Like for example, a lane divider. The problem with that is there is, for most of the data sets and models right now, no connections to traffic elements and so on. And this data set provides a lot more in that regard, and we hope that it sparks the research for new networks here. The other one is multimodal end-to-end driving, which we also have now I mean, it's not a fully closed loop evaluation if other researchers who don't drive our cars do it, but still we have a very nice occupancy layer based on our 7 LiDARs. And on top of that, we have the maps. So we can not only evaluate end-to-end driving based on like some pre-recorded ego trajectory, but actually if the driving is correct according to the map. So another thing which we all like, all these benchmarks are also like some experiments to that on our paper, which is already on archive. So you can have a look if it's interesting for you. So another new another research topic which was hot right now at CVPR is novel view synthesis. And here also we can use like the back projection accurate maps to evaluate novel view synthesis, like seeing are the traffic lights still where they should be, and so on. So that's another way how to use maps for evaluate current computer vision tasks. And finally, long-range mono depth estimation was also something, since we can provide a 400-meter plus depth ground truth. We actually benchmarked a lot of the modern models, and we figured out that the models which perform really good, some of the models which perform really good at like 200 meters and are currently like the leading models in this field, are actually getting worse with larger range than other models. So this data set is also very good in benchmarking to see which depth estimation models are really better than others. So to all of these, I could answer you more questions. I also have backup slides, but I would like try to wrap it up. I would like to welcome all of you to have a look on our data set. As I said, there's the KidScenes page where there are a lot of information. We also have like a long tail distribution part of our data set for the guys of you who are interested in that. We also have the paper ready as an archive preprint. The full data set is on Hugging Face, and you can already check it out in a very nice visualization with Voxel 51. So it's all there for you to discover. And yeah, if you have any question now or later, we are very happy to help.